Okay. Okay. All right. Thanks for inviting me. Thanks for inviting me, Professor Panda. So one of the things that I like to talk about here is how we are seeing the differences between some of the benchmarks and use cases. And so we've been working with some of the collaborators such as Saletore, GenC, and CERN, Novartis, and also with Dell EMC to see how we are some of the real use cases are. And so let me start with saying what this convergence is all about. Why there's you have heard that HPC and AI is converging, and there are what we have seen is and of course data analytics as well. But I'm going to focus more on the HPC and AI part of it, and then talk about some deep learning on how on HPC, and then how deep learning is actually displacing some of the HPC applications. So the three forces, as you see here, are driving are the scope, which is analytics and AI, and scale, which is exascale, and how that's delivered either in the on-premise or in the cloud via HPC. And some of the applications that we are finding are, if you see, are varied uses. They are all from consumer to finance to health and to industry, and this is more and more happening, and we are seeing more and more that people are actually looking at deep learning as a means of doing trying to infer, trying to predict based on models that are there, either it could be standard models or custom models. And we are actually working with partners on some of the custom models and hoping, trying to drive real world value. So what is this convergence? As you've seen, deep learning, all the benchmarks that you see start with ImageNet. Okay, a lot of the benchmarks start with ImageNet. ImageNet is a clean data set. It doesn't mean it started with that. Somebody's already cleaned it, and somebody has taken the time to clean it, all the 1.2 million images, and they have cropped it. So all that actually still needs to happen if there is an organization that has petabyte-sized data sets. So that's the analytics part of it. Now, you may want to reduce some of the dimensionality of that by reducing some of the, saying, for example, if you run a PCA analysis or some other standard machine learning analytics. So analytics has to happen. I mean, imagine automotive where they are ingesting a huge amount of data, and that's actually just raw data, and then they have to time sync with LiDAR, radar, and of course vision. So all that still has to happen before you can actually even do deep learning. So that's the analytics, and that's actually, so there's you have a huge amount of data. You don't want to move that data because it's very costly, and you want to be able to do analytics AI in the same environment. So that is already happening. So what's happening now is there are simulations, some modeling and simulation that start with some mathematical computation, such as Navier-Stokes or Monte Carlo or whatever, and that's what we're calling this inside out, and you actually generate simulations to predict what the simulations would look like. Now comes in deep learning, and then what we are calling outside in, which means that there's already a huge amount of data, and you train the machine to actually to predict the same models or data, and that may come from natural events or it can be generated, and so that interaction is now happening, and that's the convergence. Okay. Okay. I thought I did that. It's my other. Hang on. I am extended. It is. Okay. Yeah, I use this. So, so what you're seeing here is that they're all intertwined. That is HPC, data analytics, and AI. And okay, it's.
This button is for off.
No, I press this one. This one. Yeah, okay. I'll try this one. They are all intertwined, and what you're seeing here is how actually analytics and HPC can work together. There are things that are actually happening because the way you generate data and simulations, and that actually is to be able to do the analysis on that. There is also, for example, as I just said, that the data needs to be cleaned before you can actually do AI on it or some kind of deep learning on it. So that's and then this is that's the true convergence that we're talking about, is where actually AI is trying to displace some of the HPC applications, or I'm not going to say it's not replacing, but it's in a sense of trying to displace, and one of the reasons. So so the two types that we are seeing is, one is how do I use my HPC environment to create new models and then run prediction on it, or to displace some of them and then generate data, and then that data can be used, the model can be used to generate simulated data or through deep learning. So in that respect, I'm going to talk about these 4 use cases with Novartis, with Dell EMC, with GenC, and then with CERN. So let me start with Novartis. So Novartis actually came to Intel because the images were large. As you can see, the images are like about 26 times the size of the ImageNet data set. So these are large, and that's their model. That's a custom model. That's their model. And as you can see that even with a very small batch size, you actually exceed the 16 gigabyte limit what they had on the GPU. So they actually couldn't run it on GPUs, or they could run it very small batch size, and then utilization would be very low and it could take a long time. So as you can see that it went from 17 gigabytes to 64 gigabytes when you increase the batch size. Now we were able to run it on these 8 nodes of. It's not a very scaled out, but on an 8 node cluster, we were able to definitely give them the solution. Now this specific application is actually for drug design for Novartis, and as you can see, we actually were able to train to full convergence on this, and then we extended that convergence to 64 nodes on Intel Skylake, and we got a fairly decent speed up because the large images, large memory usage, to about 56% on 64 to full convergence. So that's one of the reasons, because if the memory limitation is one of the big issues what GPUs face today, and there are ways to do this. Now, one of the things that if you have a large memory, the solution is to tile it, that is to split into subsections, small, and then run it on GPUs. But sometimes that doesn't happen because it can give false positives, and that was not acceptable to Novartis. Another use case that we looked at was with Dell EMC was on chest X-ray. As you know, emphysema and pneumonia are the 2 major diseases that actually affects huge number of population. As you can see, 3 million US and 65 million worldwide for emphysema, and pneumonia was, is even larger. So early detection is extremely important. And here what we actually did was we used ImageNet data to first train the model, and then use that transfer learning rather than starting from scratch. Use the transfer learning to then run on the National Institute of Health data set. That data set was not very large. It's about 120,000 images. But however, we were able to show that if you look at the categorical, and actually this work was done, the one on DenseNet 121 was done by Andrew Ning and at Stanford. And we extended that, and we were able to show that out of the 14 categories of diseases, we can actually did better in 10 of them. And they were actually able to show only 4 of them from Stanford. We were able to show that you can actually get better on 10 of these accuracies. And actually you did better than the DenseNet 121. And then we trained it also for a large number of nodes, and as you can see, we could scale it to within 8.5 minutes on 256 nodes on Dell cluster. So that's so this is the scale that we're looking for, and in a sense, fairly good speed up on 256 nodes. This was on Dell cluster, which is Xeon on running OPA with OpenMPI at that time. Another use case is sorry, before I go there. So we also extended, so one of the things in deep learning is important is if you just talk about performance, it's of no use, because if there's a large performance and you do not get the accuracy, then it's not very meaningful. So one of the things was, okay, so we can get, as you know, ImageNet, we can get 76.2%, which is with 90 epochs. Question is now, people are looking at larger models, which is like ResNet 59, and then there is AmoebaNet small, and there's AmoebaNet large. And we actually explored to see how much can we actually get to this accuracy, because one of the things then the focus of deep learning is to actually get to like almost close to 100% accuracy, or of course better than humans. But so we actually looked at, but if you see the memory consumption, the way it's going up is like from 11 gigabytes to 43 gigabytes to 61 to 125 gigabytes, and that is the scale at which some of the the GPUs cannot handle that memories, because 125 gigabytes is very reasonable for a 2-socket Xeon system. But if you see the accuracy, of course, it takes longer, it takes more epochs, it takes from but you get beyond the state-of-the-art accuracy. Every percent or every 0.5 or 0.2% is a challenge, and getting from 76.9 to 80.9 is a fairly challenge. So we have extended that. Then also we worked with GenC. GenC have a cluster in France, and GenC is and this is a real use case. It's a plant net. People go for hikes. They take the kids for hikes, and one can take a picture of a plant. You can upload to PlantNet and can tell you what that plant is. So essentially recognition. But here now it's worldwide plant, so 300,000 K, not 1K like in ImageNet. Okay, so imagine if you know the deep learning part of it. 1K is at the output layer, at the last hidden layer. Okay, and that is 1,000. This is going to be 300,000 wide, so that's why the model is big. Also, we found out that that with that large at the output layer, it wouldn't the Google's protobuf actually crashed, because it has a limit of like about 2.2 gigabytes. So we had actually modified. We actually took ResNet 50, but we actually modified it, and it's published. We modified it so that we can actually handle close to like 1.9 gigabytes within, and that was the model that were actually used. So it's a modified ResNet 50, and this was not on TensorFlow, but this was on Caffe. It was running actually on Mellanox, and on the Irene cluster, we were able to scale it to 1024 nodes. And as you can see, that's linear. That's the PlantNet actual real data to convergence. And the accuracy actually in this case, because of a very mismatched or very unbalanced images, because in ImageNet it's very balanced. Here it's a real use case. And that's some of these use cases actually show up because those are the custom models and those are customer use cases. So with a very unbalanced, you don't see that accuracy, but it's in close to like 40%. But that's the best they could do. So that's another use case. Another use case is what I'm going to talk about is how some of the deep learning actually displacing HPC applications, and that is use the model for generating data to then accurately match the simulated data, and then you can generate, because what are you doing in simulation is actually generating data that's actually you can visualize or infer. So and this brings me back to that chart I showed where you go from outside in to inside out, and essentially there is that interaction between HPC and deep learning. So this work we collaborated with CERN, with Sophia, and then of course with Sarah. Now, as you know, CERN does high energy physics. They're developing detectors that actually can, and in the Large Hadron Collider, that actually generates particles and particle showers that actually, so they want to know what, and one of the things actually, if you know, was that the Higgs boson came out from them. And so they're understanding how detector design works and how they can generalize it to more other particles. And then of course, any good simulation demonstrate that that the physics, the high energy physics is accurate as well. So for this case, what is the motivation for doing this kind of work? So one of the reasons is if you see the inference performance is, if you were to run, and GeantForce is actually a simulation software tool that is CERN's workhorse. What they were seeing at that time was 17,000 milliseconds per shower, and we used in an unoptimized 3D GANs was that we actually looked at was 7 milliseconds. So there was this huge improvement in inference is what actually drives some of this, because if you see Monte Carlo is a heavily compute. And probably same way Navier-Stokes equation or any other equation that used for simulation modeling. So that big jump in inference is what drives some of this, is to what can we do, because their compute requirements would grow over the next few years, and they want to be able to address. They still want to be able to do all the work that they're doing in high energy physics. So for this application. One of the things that we worked with them was using generative adversarial networks, and as you know, GANs came from Ian Goodfellow, and so what is GANs? There's a generator, there's a discriminator. You feed the real data into the generator, into the discriminator, and you feed random data into the generator. The discriminator discriminates, provides feedback, gets a loss, you get the gradients, you do an all reduce on that gradients, and then you actually get to a point where you cannot distinguish between the real data and the. So you use some of the simulation data already generated, and then you build a model using random noise, and you get a model that's actually matching the real data from simulation or from simulation. Then you use that model and run in, and then you can generate particles. And those particles should be able to match accurately to what simulation would have done, but at a much less compute cost and much faster. So that's the intent. And GANs are also notoriously not very easy to train, but we were able to train this network fairly well. It's an and as you know, some of these are actually not real pictures, but they are living room pictures. They are generated by GANs, and so there is, and you know, this worked for this application. I'm not sure whether it will work for other applications, but people are exploring. So this Monte Carlo to 3D GANs is essentially these, as you can see, the discriminator and the generator and the discriminator, and these are and these are three-dimensional volumes that are actually, so the volumes were trained on so we trained the models on 25 pixel cubes, and of course they do 3D convolution, and then you develop the model. So we did the single node, and we then scaled it out on TAC, and we got a fairly good performance. Of course, the reason for performance scaling that well is because, as you can see, the seconds per epoch is fairly large, 17,000. Okay, so that, of course, you know, model being small, you're not passing that much data, so the communication cost is much less compared to compute cost. So of course, you know, as you can see, we can get up to about 95% scaling efficiency. Of course, single node performance matters every time. Just scaling 93% without single node, again, is not very meaningful, because you have to know what the cost is for scaling for single node. So we took this and so let's look at the accuracy at scale. We looked at different batch sizes. You know, from the red one is GeonT4. So these are the error bars for multiple runs. So the GeonT4 are there. Blue one is batch size 1024, and we increased it to 496 to 10240. And the interest is how close or far are we from the red error bars. And if you see a slightly zoomed in picture of that, so the interest to CERN was, okay, in that energy range of 50 to about 250 electron energy, I guess, what they call as EP, these electron E calories per electron shower, how close are they to the red? And some actually, if you see, as that some are close, some are not, but in there, this was tolerable for them. This was acceptable to them, but they are still trying to see whether actually we can train something better with more data. So the inference time, as I said, this was the old inference time, or 2500, and what's the driving force now? So and if you with further, as Intel, you know, Intel is always continuously optimizing TensorFlow, optimizing MKLDNN, and as you can see, going from Monte Carlo simulations to 3D GANs, you know, and larger and batch size of 128, and as you can see, you know, the speed up changes, and this 20,000 improvement in inference is very typical of some of these applications. And that's what some organizations are actually looking at. So these are some of the real use cases, and these are driving force. And so what they're indicating is we can use deep learning to displace some of the simulations. Of course, it's, you know, it's people are skeptical, but we're still working through it. Some more recent data is also what since the last year we have seen actually that that improvement has translated to much better performance on single node, which has dropped almost 3.5 times over. Yes. Yeah. Data parallel. Everything was data parallel. Monte Carlo actually was probably not running parallel. I think that's the way they've been using it. That's the current default way of using XeonT 4. I'm not sure whether that is probably not parallelized. But it could be. But I mean, that's their workhorse, and that's what they've been using for many years. So as you can see, of course, TensorFlow improvements, MKL DNN improvements has led to that improvement in performance. And as you can see, with lower skews of Intel Xeon, which is 6148, and almost half the number of processors or nodes, 64 nodes, is better at 132 milliseconds per epoch compared to older data, which was on 128 nodes on TAC. So this is the reason to look at use cases where actually customers are finding value. So one thing I want to present you with something that we have been talking about here. So customer use cases do matter, and why do they matter? So this is a 2x2 chart which shows the horizontal is the memory consumed from small to large on a single node, and the vertical axis is the input data size, not data set size. Data set size, because deep learning doesn't consume petabytes of data at one given time. It has to consume like in batches. So the data set this is the data size, input size. The 10 megabyte, 10 gigabyte cross is arbitrary at this point in time. So why am I showing this? So if you look at some of the data center AI benchmarks, such as MLPerf, they fall in this category. Batch size 64, maybe 128, maybe 256. Image size is 224 by 224. You have GoogleNet, which has become obsolete. There is ResNet 50, which is one of the more popular ones. ResNet 101, it's a bigger sibling of ResNet 50, gets you slightly higher accuracy. Inception V3, VGG 19, but that's the size of the memory consumed, and if you see the gigabytes range, that's what's happening. Okay, and given your GPU, whatever favorite GPU, you can see where a single GPU would actually whether it can do it or not. Now you can reduce the batch size, of course, to run on your favorite hardware. But what we have seen is, from the use cases, this is where some of the use cases are. The work we did at CERN falls here. It's still less than 10, 20 gigabytes. Dell EMC work with we have also done work on language translation or transformer model, and that's where it is. Novartis that I showed you is about there, and then Dell EMC with AI radiologists that I showed you falls slightly higher, but each data input size about 100 megabytes, but consumed data is about close to about 40 50 gigabytes. We are also working with a cancer research institute. We are also working with a university medical center. But if you see, the images are becoming larger. At least now, of course, this is little more the domain is a little more on the medical side, but there are oil and gas as well. And as you see, the memory required is increasing. So one of the things that the medical image analysis, the 3D dense CNN is a batch 1 inference, and it's a 2K by 2K by 2K, and the image size is in the gigabytes range. The memory required is actually in terabytes range. So we can be I'm not going to name the customer, but the customer is going to talk about sometime this year, later this year. But that's the kind of data set we are talking about, and these are the use cases. This is where the benchmarks are, and what we are seeing is that a lot of the use cases are actually in this large memory, maybe large input or maybe small input. Small input could be small input too. For example, the BERT transformer, which is about 340 million parameters, takes about 40 gigabytes. But the sentences are only very small. I mean, language model sentences, the input data size is very small, but the model is large. And then there's a even larger model, a larger language model, which is which is on the leaderboard, which is even larger. So however, the memory use we are seeing is huge, and so that's the difference between. I just wanted to show you that what we are seeing. Of course, we are also working with Lawrence Berkeley National Lab to see what some of the science use cases can actually be driven into MLPerf, because if those are the actual real use cases, maybe some of these should be part of the MLPerf. But right now the MLPerf is more in the lower left corner. So that was my last slide. I'll leave you with that. Okay. And if you have any questions,
Let's thank